his story, his life is very interesting, even though it's very short. And I would like to ask someone to read this paragraph about Green. And so we know a little bit more about him and this person behind the thing, okay? So I'll ask Julian, could you read this to the class?
George Green. Green's theorem is named after the self-taught English scientist George Green, who lived from 1793 to 1841. He worked full-time in his father's bakery from the age of 9 and taught himself mathematics from library books. In 1828, he published privately an essay on the application of mathematical analysis to the theories of electricity and magnetism. But only 100 copies were printed, and most of those went to his friends. This pamphlet contained a theorem that is equivalent to what we know today as Green's theorem, but it didn't become widely known at the time. At age 40, Green entered Cambridge University as an undergraduate, but died 4 years after graduation. In 1846, William Thomson, which is also known as Lord Kelvin, located a copy of Green's essay, realized its significance, and had it reprinted. Green was the first person to try to formulate a mathematical theory of electricity and magnetism. His work was the basis for the subsequent electromagnetic theories of Thomson, Stokes, Rayleigh, and Maxwell.
Wow, interesting, isn't it? He self-taught himself, isn't it? He worked full-time in his father's bakery, age 9, and he taught himself from the library book. Okay, but isn't it inspiring? You can teach yourself. Okay, so inspiring. And then he entered Cambridge University as an undergrad at 40-year-old. So never too late to start. Okay, never too late, right? So inspiring. But he died 4 years after graduation. No, so he probably is like over 40, 46 or something, right? I miscalculated. But well, he led us this beautiful theme. It's called Green Theme today, and we're going to learn about it. So isn't it interesting? As we learn about the theme, we think about this person. Okay, all right. So, when do we use green theme? Okay, first starting with a why. Why do you name it? When do we use it? Right. So I'm going to ask people to read the paragraph. Okay, I'm going to ask Angel. Could you read the first paragraph?
A computer engineer can use Green's theorem to find the center of mass of a bladder being used to build a hard drive.
Okay, great. And then Kyle, could you read the second paragraph?
An ecologist can use Green's theorem to find the area of a lake whose shoreline is described by a pair of parametric equations.
Okay, perfect. Okay. And the last paragraph, I'm going to ask Luca. Could you read the last paragraph here?
Yeah. An air conditioning repair person can use Green's theorem to determine what the heat flux through a duct should be in order to determine if heat is flowing as it should.
Okay, so those are just some example green things. Okay. So here is green things. Okay, and it's very simply stated. Okay, and the result is so beautiful, right? How can we know this actually related? Okay, so what is it? Okay, so it says that. Okay, before this, I think I'm going to give you this picture also. Okay, so look at this picture here. Okay, this C here is the boundary. It's the boundary curve of this region D. Okay, and the C here is positively orientated. Okay, well, what do you mean positively orientated? We get to that later on. Okay, and piecewise smooth. Okay, so if you cut it into, you can cut it into small pieces. Each piece will be smooth. Okay, and simple closed curve. Okay, what do you mean simple closed curve? All those new concepts, we're going to get into those in detail. Okay, and in this plane here, and let D be the region bounded by this C. So C is the boundary of D. Okay, and if P and Q have continuous partial duality on an open region that contains D, okay, so if we have an open region that contains D, and P and Q have continuous partial duality, okay, on that open region contain B. Then this line integral of P plus Q, okay, over this boundary C is equal to this double integral of this over the region D. Well, so it's kind of beautiful here because actually we relate what happened to this region, this double integral, relate to only the boundary. Okay, so this integral, double integral here, is actually determined by actually the boundary. This single integral on the boundary. Okay, and we're going to see how we use it today. All right. Now, what does the green theme here do? It actually gives a relation between this line integral along a simple closed curve, which is the C here, and this double integral over the plane region, over this plane region right here, over the D. Okay. So, and the D here is bounded by this C over here. Okay. All right. So we have this. There's some remark here. We assume that the D here consists of all points inside this C as well as all points on C. So it contains the inside, but also contains the boundary. Okay, so the whole thing, including the boundary for the D. Okay. Okay. Now we're going to know more detail of this. Okay. So we want to know what does it mean positive orientation, right? So what does it mean positive orientation of a simple closed curve? Okay. This one here is positive orientation, so like this. Okay. Counterclockwise if you trace the boundary. So counterclockwise right here. This one here is negative orientation. It's clockwise if you think about right here, right? Okay, and the way that we can think about this orientation here is when you walk along the curve, okay, follow the direction of the arrow, then the region is always on the left. Okay, it's always on your left. So imagine that you walk along this boundary, okay, like a garden, then the region is always on your left. Okay. Now this one here, if you walk along, then the region is on your right, right? So this is negative orientation. This is positive orientation. Okay. So that explains the concept of positive orientation or negative orientation. So here I say the green theme again, but this time I color coded this so you can see the relation over here. Okay. So let's see be a positively orientated, piecewise smooth, and simple closed curve. Remember last time we talked about simple curve. Okay. I can just give you a quick definition for simple curve. Simple curve, it doesn't cause itself. Okay. So if it causes itself, it's not simple. Okay. So this one doesn't. See the C here doesn't cause itself. And as a closed curve, the initial point and the terminal point coincide. Okay, so you start here and you always end up there. There's a closed curve. Okay, so this is positive oriented. When you walk along the boundary, the region is always on your left. Okay, and piecewise smooth. So it doesn't have those sharp point, corner, or break. Okay, and when you consider that into pieces, then it doesn't have any break, sharp point, those. Okay. Then, if this curve is satisfy all of this, okay, in the plane, And let D be the region bounded by this curve C. If P and Q have continued partial duality, which means if you differentiate P and Q with respect to X and Y, those partial duality will be continuous. Okay. Then what happened? Then this is actually the ninth integral. Remember, you integrate this over this curve is the ninth integral. Then this ninth integral is actually equal to the double integral of this over this region D, over the inside. Okay. D. You see the relation here? The P here. Okay. The P over here you have partial derivative P with respect to 1. The Q is this one here. Then here you have partial derivative Q with respect to X. And in between is a subtraction. Okay, subtracting that. Okay. All right. So let's try some example to understand the theme. Okay. So it's actually a very good, beautiful theme. Not too hard to. It's used so much. Okay, so we try to evaluate it. This line integral. Okay, integral of this over this curve C. And the C is this triangular curve. Consists of this line segment starting from 0, 0 to 1, 1, and then to 0, 1. Okay, I draw it over here, and then back to 0, 0. Okay, so it goes this way, this way, this way. Come back to 0, 0. Okay, so it is a closed curve. Okay, all right. So is it positive? Positively oriented? It is, right? So it's counterclockwise. It is simple. Okay, it doesn't have knot. Okay, it doesn't cause itself. So it's closed. Okay, go back to the sample. Okay, so then this is D. Here is the region that is enclosed by this curve. Okay. Well, we could actually evaluate this integral using 16.2, how we do line integral, right? So before we actually can do this, actually when we have time later at the end of class, we're going to actually do an example, evaluate something like this using line integral, and comparing by evaluate this using green sim, and you see how green sim is. They have simplified the process so much better, much shorter. Okay. Okay. Now, although we can do this using the line integral that we learned in 16.2, but that will involve setting up 3 separate integrals along 3 side triangles. So you have to find this. You have to parameterize this segment and parameterize this segment and parameterize this segment, and then later. You have to do separate integral for that, okay, and then sum them up. But that is going to be cause much tedious. So today, let's try to use green sim instead. Okay. So notice that this region D enclosed by C is simple and have positive orientation. Now, what do you mean simple region? Anybody know what it means simple region?
It's the one that doesn't overlap with itself, right?
No, that was a simple curve, right? Okay, simple region over here. Okay, I actually put it like this. I actually looked it up. Okay, so simple region is the region that is both type 1 and type 2. Okay, those regions are called simple region. Okay, so do you remember type 1 and type 2? Remember? Okay, so when we do this region on the xy plane, this is type 1, right? Okay, so if you draw a vertical line, then it's going to go from one end to the other end. And this is type 2 region, right? If you draw vertical line, it goes in one line segment, right? One nice segment there. So if it's both type 1 and type 2, that is a simple region. Okay. Now some of you might say, how can I do it? Is it a better way to see this better? I also looked this up. Okay. So a region here is x simple or y simple if every horizontal line intersects the region in a nice segment. Okay. So for example, this one over here is not simple. Why is not simple? If you draw a horizontal line right here, what happens? If you draw a horizontal line like this, right, it's going to intersect the region, one line segment over here, and another line segment here. So two separate line segments. So that is not simple. Okay, so this one here is not a type. So it is not a type 2 region, right? But it is a type 1 region though, because if you draw vertical line, any one of them, any vertical line is intersecting the region in one line segment. But if it's horizontal, then it's intersecting the region sometimes at 2 line segment like here. So this is not simple. Okay, all right. So simple, if you draw horizontal and vertical line segment, it's going to intersect at one single line segment. Okay. Okay. So this one here is a simple region, okay? Because if you draw horizontal line and vertical line, it's going to intersect the region in one single line segment, okay? So this is a type 1 region and also a type 2 region. It's a simple region, okay? And the C here has positive orientation, so counterclockwise, okay? Now what happened, we try to look for this integral, right? We're looking for this integral, but then if you do it directly using line integral, we have to find parameters. We have to parameterize this 3 line segment and we do all those work. It's very tedious. So we're going to use green theme here. So we want to turn this into the double integral of over the region that is bounded by this curve C. Okay. So here I already color coded this. So this is a P, and to the 4 is a P, right? Okay, and x times y is a Q. And what should I put over here? Inside the parentheses. What does the green thing say?
Partial derivative of
Partial derivative of
p
P
with respect to y.
with respect to
Y.
x.
Oh,
With
sorry,
respect to
sorry,
x, okay. Minus, right? Subtracting what? Partial derivative of this, right? With respect to y. Y, right? Yeah. So that was what Gracie says. Okay. All right. So that's partial derivative of this function. Okay. So partial derivative of this function with respect to x, the second one. And then subtracting, notice that this one here had to be subtraction. Okay. Partial derivative of this function with respect to y. Okay. And then this double integral over this region D. Okay. Okay, now let's do the calculation. Okay. What is the partial derivative of this with respect to x? It's y. What's the partial derivative p with respect to y? 0, because this one here has no y involved, right? So we got, this is partial derivative that is y, partial derivative this is 0. Okay. All right, and this is what kind of, well, in this case, let's regard this as a type 1 region, right? Let's think about this as a type 1 region. So when a type 1 region, so we put the dy here as this, for the inner integral with respect to y. So y go from 0, right? And then all the way to 1 minus x. So y, this part right here is y equal to 0. And then this part here is y equal to 1 minus x. So you have 0 here, 1 minus x here. And then the x over here go from 0 to 1, 0 to 1. So we got this double integral, right? And this double integral is much easier to compute than this line integral directly, okay? All right, so now let's simplify this, okay? Let's do it to continue. So what do we get here when you integrate this y with respect to y? We got
1/2 y squared.
y squared over 2, right? We got it. So you got y squared over 2, and you substitute y go from 0 to 1 minus x. Okay, so you substitute that in, and you do the calculation and follow the calculation here. The result here turned out to be 1/6. Okay, so this line integral turned out to be 1/6, and actually the process here is much easier than parameterize each segment here and do the line integral directly. So that actually save a lot of time, okay, right here when we use green seal. Okay, so that's a very neat result here. Any question? Okay, all right. So you just need to pay attention which one is the P, right? This is the P and this is the Q. Okay, here's the P, here's the Q. Okay, remember which one to differentiate with respect to which. Okay, green seal. Okay. Now the last example we did, we actually express. Last time when we do this line integral, we use the double integral and to make the process faster, right? Save a lot of work, right? Now sometimes you go the other way. So you want to actually express this double integral in terms of this line integral. Okay, and when do we do that? Okay, so last time when we evaluate the line integral, we use the double integral because it was easier to evaluate. But sometimes it is easier to evaluate the line integral, this line integral here, okay? And then a green thing is used in reverse direction. So reverse, you express this double integral as this line integral, this single integral. Okay? When do we use it? This is one example that we use it. When P and Q are equal to 0 on the boundary. So if you know that on the boundary over here, P and Q are equal to 0, it doesn't matter what happens inside the region. You just know that on the boundary, P and Q equal to 0. Then what happens here? Then this double integral over the region is equal to what? If this and this equal to 0, P and Q equal to 0, then this line integral over C, P and Q equal to 0 over C, then this line integral here will be equal to 0. Because this is 0 over C, then this line integral is equal to 0. So which is kind of neat because we actually don't know what happened inside the region. We just know that on the boundary, the P and Q here both are equal to 0. Then we can actually conclude that this double integral over the whole region that is equal to 0. So that's the time that you actually use Green's theorem to relate this double integral over the region to this single integral over the boundary. Okay? Question? Okay. That makes sense? Yeah. That actually, if you're looking at this, that actually reminds you of the second part of fundamental theorem of calculus, right? How does it relate it? Well, the fundamental theorem of calculus, when you take the duality when you integrate f prime of x, okay, with respect to x, and then x goes from a to b, okay, what does it equal to? Anyone remember? Equal to f of a, f of b, right? Subtracting f of a. So this one here, actually, this integral is only matter here is the value here at the end point, right? So here we have an interval. Okay, so the interval here is a to b. So a to b here, a and b here, those are the boundary. This is the boundary in one dimension, right? So a and b are the boundary of that interval. Okay. So this integral is actually only depends on the boundary of that. Okay. Now, what about this one? So this one says that this double integral is actually depends on the boundary, the C. C is the boundary of this region D. So it only depends on this single integral over the boundary. So you can try to think about the relation between the fundamental theorem of calculus part 2 and Green's theorem. Okay, they're actually related. Okay, this is the boundary of this function f, and here C is the boundary of this region D. Okay. Okay, so it depends on the boundary. Okay, that's one application of the reverse direction of Green's theorem is to calculate area. Okay, so we know that the area of a region. How do we find the area of a region? We find the double integral 1, right, over the region. Then we get the area of the region, right? Now last time we talked about this, right? So if you have the single integral of 1, okay, and dx, x go from a to b, that is going to give you what? B minus a, and that is what? That is the length of the interval, right? Okay. So this is the length of this interval. And when you integrate double integral of 1 over a region, let's say D, and what do we get? We get the area of the region D, the area of this region D right here. And when we do triple integral, of 1 over a solid, okay, over a solid, and what do we get? We get the we get the volume, right? So we get the volume of that solid, okay? So when you do double integral of 1 over the region, we get the area of the region, okay? So if we wish to choose, so I will look at this double integral and I try to make this function here to be 1, right? So I'm going to pick P and Q so that this expression, the result will be equal to 1. That way, when I take the double integral of this, I can actually use Green's theorem to convert that into that single integral over the boundary. Okay? So there are several possibilities. One way to make this expression here equal to 1 is we can let Q to be equal to X and P to be equal to 0. Okay. Well, when Q equal to X, what is this? Partial derivative Q with respect to X will be 1, right? And then P is 0, then you will get 1, okay, if you have this. Similarly for this, when Q is 0, then this partial derivative is 0. Partial derivative P with respect to Y is -1. Together with the negative sign here, we get +1, right? And similar for this, we got 1/2, and this we get -1/2. So 1/2 subtract -1/2, we get 1. So those are different possibilities to get this expression here to equal to 1. Okay. And corresponding to each one of this, okay, remember this is the Green's theorem, right? So when we take the double integral of this, that can turn into this single integral of this over the boundary, okay? Then we can find the area, right? This time because this part here is 1, right? So we make this to be 1, then that is going to give you the area of the region. And that area is, let's call that A. According to Green's theorem, is equal to this integral over the boundary, okay? So it's an integral over the boundary. What is that circle there? What does it mean? Anybody? I make a notation. I make a weak mark over here, the notation. This circle here, this is on the integral side right there. Or sometimes you put an arrow there, put a counterclockwise arrow there. Or sometimes you put this kind of like the partial derivative sign there, D, okay, like that. All these three means that the line integral is calculated using a positively oriented boundary curve of the region D. Okay, so those are the notation. Okay, so positively oriented. So when you put a circle there, that means it's positively oriented. And sometimes you use this kind of like the partial derivative sign here to indicate it is the boundary of D. Okay, so all three are equivalent notation. So it is positively oriented. So this one here means that this area is actually equal to this line integral is equal to this line integral, which is calculated positively oriented around this boundary C. Okay. Now this is what we define. We define P and Q this way, and we got this part here equal to 1. That's equal to this line integral over here. Okay. Now in this case, P is 0, like the first one. P is 0, Q is X. What should I put over here for the first one?
X.
X, you got it, good job. Okay, X. Okay, do the second one. P and Q equal this. What do I get for this side? What should I put over here?
Is that the same?
P is negative y, right? Q is 0. So I should put a negative y there, right? Okay. So negative 1. So I put the negatives outside and the y here. Okay. What about the last one over here? What should I put over here? Let's put this function, right? P is negative 1/2 y, Q is 1/2 x. So we can actually take out the 1/2. Okay. So P is negative 1/2 y. Yes. P is negative 1/2 y. Q is 1/2 x. Right here. Okay. From this. So these three, those are the, let's call it formula 5. Those formula give you the area of the region D, and only depends on, so it is a line integral of either one of them, any one of them is going to work. Okay, if you try to, so what happened over here is, so if you have a region, a simple region, okay, so let's say this is D. The book actually have a very nice picture. They actually have an island in a heart shape. Okay, imagine this is an island, right? Then what happened here is you can actually take any one of these three to calculate the area inside area of this region by taking the integral over the boundary. So if you know the boundary, then you can actually find the area over here inside. Isn't that cool? Okay, question? Okay. So I actually try to show you a picture. Okay, so you see this island over here, right? So you see that island over here, right? This is in the heart shape. I wonder where is this? Okay, let's see the fingerprint. I can't see the fingerprint. Okay, do you know where is it? But anyway, it's so interesting, right? It's a heart shape, right? So if you want to find the area of this island, right? You can see the line integral, one of those line integral over the boundary. You can actually find the area that's enclosed by that boundary. Okay, so that's kind of interesting. So that formula we just have, right? This formula 5 over here. Okay. This is the formula. Let me use to explain how parameters work. Okay. Can I ask someone to read this paragraph? Okay. Mia, could you read this paragraph from here to here?
Formula 5 can be used to explain how planimeters work. A planimeter is a mechanical instrument used for measuring the area of a region by tracing its boundary curve. These devices are useful in all sciences. In biology, for measuring the area of leaves or wings. In medicine, for measuring the size of cross-sections of organs or tumors. In forestry, for estimating the size of forested regions from photographs.
Okay, very good. Parameter. Anybody have any idea what is it? Let's take a look. Okay? So you see. So you move around the boundary. You move around the boundary there, and it actually can give you the area of that. So suppose this is like a graph of the maybe a forest, right? And then you move around the boundary, it actually gives you area. So on the airplane, maybe you can see the boundary, right? And then you can find the area of that region. This is kind of neat. Okay, so here's how it looks like. Here's a parameter right here, okay? And the pole is fixed. Okay, so you can start with that. Okay, that's how it works. So you trace around the boundary, and you can find the area. Okay, kind of interesting. Okay, Now we have this extended version of green theme. Rather, the green themes we only prove that we actually didn't prove it. Okay, we only say that for the case where D is simple, right? What does it mean simple? Last time we said that. Simple is that it's both type 1 and type 2, right? So when you when you have something like that, then this is simple. When you have horizontal line, then it's going to intersect the region in one line segment. And if you have vertical line, it's also going to intersect the region in one line segment. So this is simple, right? Okay. Now this one here is not simple. Why? This region is not simple because if you draw a horizontal line over here, right? It's going to intersect here and here at two different line segments. So it's not a simple region, right? So how can we make this a simple? We can actually divide this, okay? Put a vertical line over here to divide that into two regions, D1 and D2. And this D1 and D2 both are simple, okay? So we can do that. Now, when we do it that way, then notice that for this vertical line that are divided, we're gonna go in this counterclockwise direction and go up like this. Let's call this C3. Then the other way, I'm gonna go back down here is the opposite of C3, so it's negative C3. Okay. Then what happened here is the boundary of this D1 is C1 union C3, right? C1, and then followed by C3. And the boundary of D2 is C2, but it goes this way, so union opposite of C3. So we can apply green theme to both this region and this region. Okay. So the green theme applied to this region, D1 over here, is going to be equal to this. Okay. Equal to this integral over C1 union C3. And this integral over this boundary of D2, which is C2 union negative C3, this one over here, is equal to the double integral over this region D2. Now, what do? We can sum these two equations. If I sum this side, what happened to this C3 and negative C3? When we do that, they cancel out. So we get is this integral over C1 union C2. Okay, so the integral of this over C1 union C2. Okay, what about on this side? On this side, you have D1. Okay, this is over D1, this is over D2. When you sum them together, D1 union D2 is D. So it's a double integral this over D. Okay. But then we know that C1 union C2 is just a boundary of D, right? So green theme will also apply even though this region is not simple, but it can be divided so that each region will be simple. So if it's a union of simple region, okay, then the green theme still apply. In fact, that we can have green theme for any finite union of non-overlapping simple region. So, for example, in this case, you can divide this, and this into 1, 2, 3, 4 regions, and each region are simple. Then you can apply green theme to this region. Okay, so even though it's not simple, okay, so as long as we can divide it in as a union of simple region, then we can do that. Okay, still apply green theme. Okay, now let's look at this example. We try to evaluate this integral over C. Now, in the past, we already talked about why this one here is not simple, right? This region is not simple, but we can still apply green theorem, okay? Because it is the union of simple region, okay? Now to do that, okay, let's express this region, okay? Express this region in, well, it looks like it's circular, right? In circular shape. So it's better to use polar coordinate. So how can I express this region using polar coordinate? R and theta.
1 to 2.
R go 1 to 2, and then theta go from 0 to pi. Yes. So 0, 1, 0 to pi, right? Okay. So we got this region D. Okay. Then when we try to evaluate this line integral here, we can turn that into this double integral over the region. Okay. So, well, which one is easier to calculate? You think this one or this one? For this one over here, you actually need to parameterize this segment, this one, and then this one, 4 segments, okay? And the work will be very tedious. However, this double integral over the region, okay, because this region right here, it's actually much easier, okay? Now let's try to do that. So that's equal to this double integral of what? Do you guys remember green theorem? Possibility of what? With respect to Q, which is 3xy, 3xy, yes, 3xy, okay? You guys, Q, okay, yeah, it's very cute, okay. All right, so this one here, what should you put? Y squared, yes, y squared right here, okay? So partial derivative this with respect to x is what?
3y.
3y, yes, you got it, okay? And then partial derivative this with respect to y is 2y. So subtracting, we get y, right? So we get y. Then we just need to integrate the y here over this region. It's a very simple double integral, right? Okay, how do we do that? Because the circular shape, we use polar coordinate, right? So y here we have to express in terms of r and theta, right? So in terms of r and theta, y equal to what? R sin theta, very good, okay? R sin theta, okay. All right, so that will be r sin theta, y is r sin theta, and the dA here we express as r dr d theta, right? R go from 1 to 2, okay? R, see, remember the R can go from 1 to 2. This is 1, this is 2. R go from 1 to 2, right? And then theta go from 0 to pi, right here. And then you can separate this double integral in as the product of the two integral because this is a function of theta only, this is a function of r only, so we can write this as a product of these two integrals. And you do the calculation, turn out to be 14 over 6. Question? We can actually extend green theorem to region that has hope, right? This is a region that has hope right here, okay? So last time we talked, so certainly it's not a simple region because you see horizontal and vertical line over here, this intersect are two separate, okay? So how can we do this, okay? So maybe I ask someone to read this, okay? Can I ask Corinne? Corinne, could you read from here to here? From here to here?
Green's theorem can be extended to apply to regions of holes, that is, regions that are not completely connected. Observe the boundary C of the region D in figure 9, consisting of two simple closed curves, C1 and C2. We assume that these boundary curves are oriented so that the region D is always on the left, as the curve C is transverse.
Okay, very good. Okay, so for the C1 here, the outside, so that will be counterclockwise. But then C2 inside, this is also the boundary of D, but we make it clockwise. Why? Because if you walk along, right? If you walk along this path, think about it like a garden. It has to be, the region has to be on the left side, right? So this has to be counterclockwise, and then this outside one has to be counterclockwise. Okay, so clockwise for this, counterclockwise for the outside. Okay, then the two curves are positively orientated, right? Okay, then what do we do? So we actually use the trick that we did before. We're going to divide that. Okay, we divide that. We draw horizontal line here to divide it into two regions. This is D prime. This is D double prime. And when we do the double integral over the whole region D, then we can write it as the double integral over D prime plus the double integral over D double prime, like this. But then because this region over here is actually a finite union of a simple region, so we can apply Green's theorem to D prime. So this double integral is equal to this single integral over the boundary of D prime right here. And then similar for that one is equal to the single integral over the boundary of D double prime. See, remember this sign over here? This sign here kind of like the partial derivative sign. This stands for the boundary of D double prime. Okay. So we actually can, so for them, when you sum this two, the boundary over here, when you sum the boundary of D prime and D double prime, because these two are opposite direction. When you sum that, they will cancel out. Then you just get the boundary for D, okay, right there. So Green's theorem will hold, okay. So C1 plus union C2 is a C, okay. So it's going to hold even for region that has hole in it. So that's pretty cool, isn't it? Okay, we're gonna do some practice problem. How about we take a 10-minute break and we come back.